Okay, so good morning everyone and welcome to the final day of this little workshop. But a recap of last day a bit. Well, the most important thing was the Vlasiator data outputs. So we have several of those log files, diagnostics, and then the actual data in the vlsv files. And yeah, homegrown data format, and might need some getting used to, with several different grids like the Vlasov grid, so the spatial grid that can have mesh refinement, which is different from the field solver grid, which is uniform and high resolution everywhere and a bit heavy to work with. And if you use the field solver variables, then you have to keep in mind that those may have different centerings, so being phase averages or edge averages, and still possibly shown as cell values, which is a bit can be a bit misleading. And when you read data from the vlsv files, you need to keep in mind that the data might be ordered in the file a bit differently. So if you read the whole block of data, you might need to reorder it for it to make sense in plotting and so on. But the Analysator tools, for example, handle quite a bit of that for you in plotting and so on. So if you really need to access the underlying data, then that might be more, and then it might be more relevant. And yes, Analysator it has this nice Python interface for programmatically accessing the data and analyzing it. And then we have the other tool in use, which is the Visit with the plugin to read the vlsv files, which is, yeah, it's nice for interactive data explorations once you get it working, which might not be trivial, as we saw yesterday. But today's program, and we were thinking this could go like so, that first we'll go through the Vlasiator projects that we have in the code base, and try and spot some interesting case that you would like to run out of these projects to have a look at. And then we would do some workshopping and go to breakout rooms, divide ourselves up a bit, and then look if we can get you a test run chugging along. But that's for the latter part of this day. And the second, after the coffee break, we'll go through a rough draft of how would we look at doing a Mercury 6D run, and is it feasible to run, and at which cost? Like a very rough estimate on that. Yeah, then the workshopping part comes after that, and we'll conclude with some feedback and contact details on our side. Like how can you ask for assistance if you want to keep going with the Vlasiator. So let's get into business. What are these Vlasiator projects? And this is a bit of a terminological thing, that the projects in Vlasiator are these modular components of the source code, and those kind of give you the initial conditions of the run. So you set the background magnetic fields and so on, and the plasma conditions. And they also serve as template configurations. So you can find these example configurations which have the boundary conditions then listed separately, because these boundary conditions are coming from a slightly different class of functions, well, different classes. And some projects, I think there was one that actually used these runtime hooks that are in the code. Well, one of them, I guess there's only one implemented anyway, but you can, with a project class, with your custom code, you can actually hook into the runtime simulation and perform some analysis or whatever you want to do. And that's kind of nicely modular thing then that can be plugged in. And as an example, the flow-through configuration that we have been looking at, our benchmark case, and how the project is represented in this configuration is just the project keyword here. Each configuration has one and only one project. And then you have the project category class variables here set up separately. Now, this is sort of self-explanatory, but you can get all of these help texts through the Vlasiator -help command, and then grep for a flow-through or whatever project you want. And noting that here is the syntax, so you have flow-through. So this is the name of this header here, and then .bx, this component argument, which is by default this is equals 0. So here it's equals 1 Tesla in units of Tesla, and magnetic field component given on the x-axis there. So similarly with the protons, the initial density, velocity, initial moments for the plasma are given here. And yeah, this is a bit boring, but there are some options that we actually didn't use in our test case. And if you check the help output, you can find these guys. So density model, density width, and raw base. And these are then extra features that give, for example, the density model gives you a plasma density model. So this is kind of the spatial distribution of plasma density in the simulation. The other moments are then as given. You could actually do a custom density model which would hook up into the velocity space coordinates as well, but this is as it is, these are just real space coordinates, and there are some others like square signal. So you have a constant density at this raw base, and then you have on top of that you have a square signal with a given density, and a triangle wave, and so on. So this is basically a test case for solvers and so on. But there are some other things that we haven't tried with this test. And those were those. And yeah, sometimes you want to have a look at the project's code, source code. So let's go to the flow through here. Zoom in a bit. And here you can, for example, find the listing of density models somewhere here. Maxwellian sheet, Maxwellian square, triangle, sine wave. And those are hooked up here in a function that gets the distribution value for the velocity distributions at given coordinates. X, Y, Z, velocity X and Y and Z. And here, if you want to go into the details and see how those are implemented, then you are welcome to. But yeah, these are basically Maxwellians with some spatial profile. And we could also look just a bit at the project code structure. So what do these projects do? Let's take the header file here for a bit more condensed view. And what they have is functions to define the parameters that you use in the config files. some initialization stuff and set a function to set the magnetic field in the domain. So both the background and perturbed magnetic field components, as well as this function to get the distribution values and the phase space density. So these are related. I believe this one is the one that gets called from the project system, and then this calls this one or the other way around. And that's basically it for this one. There are more a bit more complex projects, but this is basically what you have in these. And for example, the project folder for the flow-through contains these guys. So there's the actual C++ code and the header file that we just had a quick glance at. And then there's an example configuration file. And so maybe some other necessary data. So this is the SolarWind input that can be used from the example config then as a boundary condition. And yeah, if you go and start browsing the project folder, you can see that some of these projects may have documentation or helper sheets that might come in handy. Some do not, which is a bit unfortunate. And I put up a list of well, a quick short listing of these projects to the study materials as well, so you can go and check that out with some quick notes on what these projects are. Yeah.
For the scripts that we just saw,
Yeah.
it just sets the conditions on the distribution function. It doesn't set the geometry or the boundary conditions or anything.
Yeah. So the boundary conditions and the box geometry, those are given then in the configuration file hooking up to different classes. With the projects, you can have, for example, then forced refinement regions, and we'll have a look at those later for the magnetosphere project, for example, because that has defined regions that, okay, we want to have accurate grid at these regions, like on the magnetopause and so on. So those can be defined in the project as well.
Okay, so if one wants to make a totally new project, for example, for the Mercury run, they wouldn't only have to provide those 4 or 5 that you just showed. The adjustments to other parts of the code have to.
You can, well, the examples that we have done with Mercury have been using the magnetosphere project, because that has the background dipole field that's given. And then the boundary conditions are then defined in the configuration file, and they hook up to indeed other places then. But you can have this configuration file that is a good template for then doing your own configuration. You can, I would say that magnetosphere would be a good candidate for using the magnetosphere project would be good for doing the Mercury run. And then you just branch off of that if you want to have some extra coding done for Mercury. But I don't think that the Mercury projects would need. I don't think Mercury would need another project as we define it here in the code. But that could be the magnetosphere project, and then maybe what would be needed would be some different boundary conditions for like the resistive planet and crust and conductive core, and that's not quite what the project system does here. So let's go through these, and then we'll go through also the magnetosphere configuration as an example to see how this works. So I have here now, a bit of the listing online as well. So we have a big bunch of projects that all give different sorts of initializations and example configs. And most of these are some forms of tests. For example, Alpha wave tests and diffusion tests, and some dispersion tests, which have been then superseded by other projects with slightly different initializations. And here I have mentioned that this one has the hook for being running functions during the simulation main loop. And then there are examples which have multiple Maxwellian distributions in velocity space with some perturbations. These might be interesting for some basic plasma physics, and various different shock setups, which I don't actually know that much about, and there's scarce documentation on these. I believe Markus has been using this IP shock at some point, so we can probably have a breakout room on these if wished.
I can chime in if you want. I have been using it a little bit.
Okay.
But yeah, so it's a setup for building shocks in a box. And we can use some scripts to set it up in the Hoffman-Teller frame. That's the usual way we've done so that the shock doesn't move out of the box. It can be used in the 1D configuration or in the elongated box with a like 2D or 1D, 2D or 3D. So it's the initial setup is logically 1D, but then you can extend 1 or 2 dimensions to have more transverse space. At some point we had some flags to add some noise as well, but so that was used for simulating shocks in a box. So that kind of test tube, shock tube, what's it called, these very old type of plasma simulations, but yeah. So IP stands for interplanetary here.
Isn't that the latest one that has been used?
Yes.
I think these were like older tests from for certain Kempf's master thesis or so.
Yeah, then it was Kempf.
True.
Yes. Okay. I didn't remember they were mine, but IP shock is the one which should be used these days for modern support of shock simulations.
I mean, if you simulate like.
Sorry, we didn't hear anything from the room. I assume you just got a question.
Oh yeah, the microphones are somewhere. Yeah. So the question was that can we simulate ion scales properly with these shock tests? And I mean these are more of local simulations. So it's basically up to the user to which resolution do you want to go. Not sure how.
The big advantage here is that we don't get a dipole which kills the time step in a small region. So you can afford a lot better resolution and bigger box for low cost compared to the similar amount of cells afforded in the magnetosphere simulation. So
yeah, and probably and because it's local, you can focus on this topic matter more, so the actual shock, and you don't have to have all the other global sheet physics and then the tail and so on as well. So you probably don't need as many cells then, but if you want, you can have the resolution then at the shock. So.
And actually, now that we have AMR, dynamic adaptive mesh refinement, I think this would be really nice. I don't think any one of us has run an actual, not just for debugging purposes, but like an actual shock simulation. So Marcus has run a lot of those, but I don't think any one of us has done it now that we have adaptive mesh refinement. So I'm pretty sure you could get some pretty cool stuff out of that with adaptive mesh refinement as well.
Yeah, I mean that's kind of the mesh refinement scheme that we would see, or we have seen in the flow through benchmark here. Just that if it's
yes, I mean we've done it
stationary
in
shock, then it's much nicer
for
even.
technical testing purposes, but we haven't done
Yeah.
it with actual science in mind so far.
Yeah. So yeah, that could definitely be interesting with AMR. And then we have some more tests, solver isotropy tests and so on, and these Riemann problem setups. I'm not sure if those are very useful, especially with kinetics. And then maybe some more interesting ones that we have listed here, like Kelvin-Helmholtz project setups. This one, what that is now in the master, might not necessarily be in an equilibrium state with there's how it was density or temperature differences over the boundary, and there are ongoing studies actually by Verti Tarvus, who has improved on this setup and is preparing articles and his PhD out of these projects. So here is definitely some activity going on. Harris profile that we have that one. This is a 1D, yeah, MHD Harris type of a profile. It has not stayed in equilibrium. We have a kinetic physics, so that's probably one part of it. And we had a 2D setup of this, but that had some weird issues, and that was scrapped. But we have one former postdoc who did do some tries with the 2D configuration, and those can be found somewhere if that's up your alley. Fire hose instability tests. So that's another example of basic physics that you could test here in hybrid ion regime. And then we have, of course, the magnetosphere project that is the main target. And just to note that at this moment, I think the example configuration in this project folder is a bit outdated, but the folder in the samples directory is a bit more up to date. And what we have in our project folder, this ionosphere 3D, that has now the ionosphere also included, the ionospheric boundary condition. But that one is definitely not a great configuration for the magnetosphere, but something to have a glance at. So let's go through this magnetosphere project a bit, as in the configuration that we call the magnetosphere.cfg. This is the kind of the terminological thing that now we are kind of talking about some like study that uses this magnetosphere project and whatever else goes into this configuration besides the magnetosphere. The sample file has a setup that is pretty approachable. So you can start the testing with some 10 nodes, which is pretty nice. And I guess these were like on the order of 100K CPU hours if you want to run it to kind of a quasi-stationary state. But to begin with, yeah, we defined the magnetosphere project that this configuration hooks into this one with dipole configurations and so on. Dynamic time step that we want to use that one. Just a proton population to be simple. Memory bailout, so we are keeping track of the memory. So if we have memory usage going above this per node, then we save the state and gracefully exit. so that you can request more nodes for restarting the run then, or just restarting the run and see if there's been some memory leak or something in communication buffers, which has happened. Hopefully not that much anymore. And for this guy, there is a static refinement. So it's just at this point just saying that we have 3 iterations of refinement that we are limiting this setup to, with some maximum radius beyond which the refinement system is not active. And some input-output definitions, diagnostic byte interval, 1 second. We probably want to have something like this, pretty frequent. We are not dumping an initial state. We are not at this point interested in that. Might be worth it if you are developing a run and seeing something weird happening, to check what is going on. Restart wall time interval in seconds. We print out 2 restarts per run and then we exit. And 10-second cadence for reduced data writing, and some stride to store some velocity distribution functions for each of these files. Then a bit further, we find the grid builder, and this gives now the geometry, at least the initial grid. 51 cells on this base grid in X direction, 40 in Y and Z, with some given dimensions here. We want these to be cubical, as we saw before. If it's not, it will complain and not run. Maximum time to run 1000 seconds, so that's a good cutoff for the test. That's about when we reach kind of the phase when the initial transients are about all gone in these terrestrial magnetospheres, at least the biggest transients. And for science cases, we keep on running a bit in the production runs. We keep running a bit further, like 1,500 seconds, or could hopefully longer. But then it starts to be a bit expensive, and it's kind of a diminishing returns at that point. Definitions for the protons, so the velocity space. This is a bit coarse, but it's a test case. But this is, of course, related to in relation to the temperature of the population, so that's good to keep in mind. But this is probably a bit coarse for the temperatures that we usually have for the protons. And some sparsity threshold for you to adjust. This has been found to be decent for these Maxwellians that we use. Your mileage may vary, and you should keep track on the sparsity. So if you are adjusting that or using widely different distributions, then it's worth having a look that you are not just removing half of your mass or something suboptimal. And on the other hand, you don't want to have too many very empty cells in the velocity space either, so you have to kind of balance that. Then we get to the actual magnetosphere configuration, and this has now quite a bit more of these settings. So if we want to have there's one setting for a constant background magnetic field in the whole domain, so that's basically now given as the set component of the southward IMF run. Some dipole settings. So dipole type, this I think is the vector dipole implementation. So vector potential that is then used to extract the magnetic field components for the background field to get a current-free field that actually cuts off before the front wall given by some configurations here. So there's a gradual decrease from the ideal dipole to no dipole at all at some distance from the Earth to the sunward direction. There are some other settings for the dipole. This has worked pretty well, so we use this one, and you can also include a dipole tilt if you wish. We haven't been doing that because then the parameter space has again a couple of more axes, and then it's you'd always have to choose something, and we don't want to go there. We are content enough just looking at no tilt and very simple solar wind, so purely southward or purely northward that is coming up soon, and so on. And here then we have the refinement settings. So we have some shells of level 1 is the first spherical shells, couple of them, and then we have the finest level 3 set up here that has some radius and some cutoff for a nose cone, well, a spherical section, and then we cut so that it just has the nose on the day side. Or as in this case, we just have the full spherical region here. So this is what these parameters look like. And this has this sort of a tail box defined as well, a height, width, xmin, xmax. So this guy here, and this also induces some refinements next to it. So we have this sort of a outflow here of or this kind of a buffered zone of higher resolution things. And this is so that we have some final resolution in the tail current sheet, which is nice. Nowadays, of course, we can have the adaptive mesh as well, but we can still use these guys as the initial grid to have a bit better refinement at the inner boundary and so on. Then the setup for the boundary conditions comes through the boundaries, and this is indeed a bit separate from the project class in the Vlasiator source code. And this is pretty simple to set up here. So periodicities of different phases, and then we have outflow boundaries set up for the protons here on these phases, and a Maxwellian boundary is here, and that we set up here to be on the plus x phase, and some setup for the proton population, so pointing to the file that contains the moments that we want to use. And then we have the ionosphere, which has its own settings a bit further down, and there's plenty of them. So this functions as the inner boundary of the Vlsov simulation domain. With some radius, we are about at 5 RE at this moment. Well, here actually is the Dawn mapping radius. This is the ionospheric altitude. And then there's this sort of a triangle mesh using some cool Fibonacci mesh type that can be refined. And we can give some polar cap refinement latitudes here. So we can get better resolution for the ionosphere as well, where it matters. And yeah, this we can discuss later. I'm not quite sure what all of these actually mean. But then what matters is, for example, the downmap radius here. So we take the field aligned currents, for example, from this radius and map along the magnetic field lines from the simulation domain from this radius to the ionosphere to extract the field aligned currents. And that should be a bit above the inner boundary, since then we couple the ionosphere back to the simulation domain by this system here, or this parameter, and this one that we now use is forcing the populations, the ions, to have such moments that they reproduce this E cross B drift coming from the ionosphere. And we have a runtime field tracer, because that is indeed required to have the ionosphere down mapping working. So here are the parameters, and Jan has also included this to modified this to try and find flux ropes in the domain, since if we are tracing field lines, we might as well trace them everywhere and see if we can extract anything useful out of them. Then we have the population settings for the project. So here we can get the initial populations with some temperature, density, velocity. So solar wind velocity here, or velocity matching the one in the solar wind. And then we introduce this sort of a taper. So we want to have a smooth initialization. So at the inner boundary, we have these ionospheric population parameters, which are, so where did yeah, here. So zero velocity, density and temperature there. But we want to map from these moments to these solar wind-like moments smoothly, so we don't have any extra shocks during the initialization, which could break the run. So we select some radius below which we are in the ionospheric regime for this population, and then some smooth transition function up to this outer radius, after which we will be at constant values of these moments. And this is to drive the initialization smoothly. And once the initial plasmas are gone, then it's also a good sign that we are in a nice science-ready state. Ionosphere population given here, and then the load balance algorithm. Yes, for magnetospheric runs, the RIB has been the best performing, at least so far. Let's see if we get any updates on some fancier algorithms. And that's almost done. Field solver, we want to have some configuration for that. So we have here the CFL conditions. So we want to stay in this sort of a range for the field solver and wave modes that are calculated in the code. We can allow for the field solver to subcycle. So we can if there's fast modes, then we can subcycle the field solver a bit, and well, 50 times is quite a lot. That can happen near the inner boundary, for example. And since we have the electron pressure gradient term in the electric field, here we actually define that, and we basically have polytropic electrons, and adiabatic is what we use normally. Isothermal works as well, but you just need to define this here. And for it's fixed, yeah, for now at least. I'm not sure how that would work, but yeah, suggestions are welcome. There's I know that there's at least there's Jan saying something. Yeah, go ahead.
No, I'm not saying something. I'm just raising my hand. I just wanted to comment on the field solver CFL. The field solver, by construction of its algorithm, is stable up to 0.5. That's why we put these values. It is metastable at exactly 1, but that works only in theoretical setups. So don't try to set the CFL to higher than 0.5, otherwise the field solver will go bust very spectacularly. And I didn't hear the question you got, so I'm not sure if I'm qualified to answer that.
The question was if the electron polytropic index is constant in the domain, which it is.
Yeah.
But yeah, how would we go about changing that? I mean, there are some interesting things that you could do, like some hybrid models use they actually solve for the electron energy equation. They propagate that as well, like IKEF. That could be interesting, but yes, yeah, they would indeed need to do something with the heat flux. I don't know how they do it. I still haven't seen what they actually do with the heat flux there. This is I think that is in Braunschweig in some master's thesis hanging about in the library. But that's yeah, that could be interesting.
Okay, and another thing that would be interesting as well is to have an empirically driven value for the polytropic index and have it changing. Let's say if one simulating shocks across the shock values would be closer to 1.4 than the adiabatic value. And then upstream and downstream one could go back to the adiabatic value, similar to magnetopause and other
that
discontinuity.
Could be indeed interesting to see how that would work. I mean, I guess like if we want to do some adjustments to the field solver, like computationally that wouldn't be extremely bad. Even so, it's like definitely there's potential to add things there, and like the electron energy equation thing that I know that is pretty relevant when you go to like cometary environments, because then you have lots of interactions with the neutrals, so you have cooling terms for the electrons and energy coming from photoionization and so on. So there's quite a lot of energy transfer for the electrons going on. So that's where I have encountered that, and that's not sure how much that would affect the global dynamics, but that's definitely something that can be looked at some point. And then Vlasov solver parameters. A bit of a margin for the CFL here. And then we can subcycle the semi-Lagrangian acceleration solver as well, but we are constraining it to the 22 degrees. And then that's the set of these slides. So we can have the coffee, which is already there. Or if you have any questions at this point, feel free. Ask them, or we can just keep it more free form as well. And yeah, please have a...
Yeah, I can.
Go ahead. Yeah.
When it comes to the adaptive mesh refinement, it's a very interesting approach to save on computational time and computational resources. But one has to initialize a mesh at the start of the run. How would the initial mesh that you use affect the dynamics later on? For example, at certain regions, if you choose a coarse enough grid, you would lose some sort of dynamics. And then even if your adaptive mesh refinement focuses on this region, you would lose the initial conditions that would drive any future instabilities in the run. So do you deal with that?
That is a very good question. we'll see. is the answer. I don't think we have done such tests at least, but it's yeah, that is an interesting point. I don't know if Jan or anyone online has any insight on this. I mean, definitely.
Jan, one possibility would be to, if you're worried about losing instabilities from the onset, would be to refine the whole box and then see where it coarsens. Of course, you'd have to be careful that it doesn't coarsen the box before your instability rises enough. But we're actually kind of at the beginning of the progress. So we have a colleague who's defending his thesis in 2 weeks, and his work was looking at some instabilities which we don't resolve at some resolutions, but resolve at others, and how to include those as subgrid models. From another aspect of our research, the current state of the adaptive mesh refinement is that we look at gradients. So we're trying to find shocks and interfaces. And we're looking at current sheets because those are useful for detecting, well, current sheets and reconnection sites. And that's the stage we are at, and we are running the first production run with these settings to see how that behaves. An avenue of research would be to try to know beforehand whether we're going to have some instability possibly in some area and refine preemptively, but that's something we haven't even started putting thought into. But since we have the velocity distribution, so the stage we are at, some colleagues have been looking at distribution functions and seem to be seeing certain types of distributions occurring in certain locations before a phenomenon occurs, before reconnection onsets. So if we find this kind of insight, we can then try to parameterize it eventually and say, if we see a hot beam, then we know they're going to go unstable. We need more resolution, crank up resolution in this region. But that's a thing we're not there yet, but we'll be keeping an eye on.
And in general, I would say your question quite nicely highlights what the difficult part about adaptive mesh refinement is. It's not refining the mesh. I mean, that's just the technical process in the computing code, but figuring out where to refine and when to refine and what to do then on the interfaces. And all of these are questions that require physical insight, because in any way, when you're forcing a mesh, you're throwing away information, and you want to throw away the information that you actually do not care about, like resolution at the edges of a domain that we know flows out in. And so, yeah, your question highlights exactly the right aspect there. We'll, for any sort of physical system that we want to simulate, we need to figure out what is it that interests us and formulate that as a refinement criterion in an appropriate way. Gradients typically are very interesting because that's where the interesting physics starts, but that's not necessarily the only.
Very interesting. Thanks.
Right.
Also,
all right. I think we are back on time. So we'll see how we can approach this next. And we have people online as well. Not quite as many as previously. But yeah, let's go through now a bit of a rough draft on what sort of computational resources you would need to do a 6D Mercury run. And this is going to be quite a rough draft. And then we can maybe iterate on that a bit more in workshopping. There's like how would a global 3D Mercury run look like for us? There's some asterisks here. So the inner boundary conditions. So we have basically a copy condition that can be used. It's might be a good first approximation, but having this sort of a resistive crust conductive core is what is being used usually. So that would need to be included if you want to reach up to the like the physical fidelity of other simulations. But let's not get hung on about that and do a hypothetical calculation here. So about Mercury, the planet itself should be about the inner boundary, and it's at 2.4 thousand kilometer radius. And the nice thing about Mercury is that the global dipole there is much weaker than the Earth's. So there's a dipole scaling factor that we can actually use in our magnetosphere configuration to just scale our dipole relative to the Earth. And I think we have a slightly different value here on in the code. So there's might be a bit of a discrepancy here, and there's a bit of variation on how the dipole of Mercury is being modeled in simulations as well. And there's really no ionosphere, but there might be some trace ion populations. Might be interesting to look at, but let's not worry about those and do the zero order thought process here. Let's look at what people have done previously. So Riku Järvinen did this Mercury ULF study 2020 with this hybrid peak model with some 13 million grid cells on this base grid. This is a uniform grid, by the way, with some 16 Mercury radius extents. And comparing this with the spatial grid of the 6D production run, this is actually more cells, but we can coarsen our grid, so that's not an issue, which we will see soon. Compared to the grid cell size, we want to have our inner boundary in this hypothetical simulation resolved at good enough resolution so that it's actually spherical and not just some Lego block. Well, Duplo block Legos it might still look like, because we still have a Cartesian grid. But we are inner boundary in the current runs is up at about 5 RE. And if we look at what our resolution is at the inner boundary, it is 2000 kilometers, which is pretty much the same relation to our inner boundary than in this study for Mercury. So we can kind of look at this Palmroth et al. Paper or the simulation for some scaling things. And yeah, there's the choice of the resolution. So let's prototype it based on this resolution and have the inner boundary resolution at this about this value. But since this Palmroth paper has one more grid refinement outside the inner boundary, we could actually get max resolution of 80 kilometers or so. And as we look at the 6D run that we have done, that has some 4 million spatial grid cells. But indeed, if we coarsen our grid in this Mercury case, that we could go down. And if we look at the highest resolution that we have in this Palmroth run, we would have, well, on the field solver grid, we do have like this 5,500 million cells, which is quite a lot. But scaling this down, assuming similar characteristics for the refinement geometry, we would get away with something like 100,000 spatial cells for the hypothetical Mercury run. And let's bump that up a bit to 200,000 cells on the spatial grid. That's like 10% of this EGI run. And if we look at some other test runs like this EGE, this is in the example data category. That has a bit more spatial cells even. So the ballpark for the spatial cells seems to be quite manageable, smaller than our test cases, or at least some of our test cases. But let's look a bit at the solar wind at Mercury, which is a bit more heavier than we have here. In this study, we don't really do this solar wind in our current runs. We are now one is going to be done soon with this sort of a nominal solar wind velocity. But that has, for example, shown some new issues such as numerical heating if we have two cores velocity space resolution and then some artifacts coming from that. This backflow into the inflow boundary, which is not great and starts to accumulate errors. So we kind of have to should be a bit more careful with the velocity space resolution here. So we can calculate the thermal velocity here for the solar wind would be something like 60 kilometers per second, and 1/3 of that would be 20 kilometers per second. And the density is also quite high, so that's more than we are used to. And not looking at the alpha particles, we could have those, but 0th order, not going to bother. So let's then maybe do a bit of a risky scaling here to compare the ratio of the velocity space resolution. So if we increase this a bit, then we get something that is comparable to our production runs. And assuming we do a bit of scaling of the sparsity threshold as well, along with the comparable to the density change in the solar wind, then we can throw out a ballpark statistics that we would have about 100,000 velocity space cells per spatial cells on average, and that's what we about see in our runs, and that's probably something that we would try to aim at here as well. Might be a bit bigger if we need to reduce this resolution to this sort of a nominal configuration, but let's run with this estimate for now. So what does that mean for our simulations? Yeah, let's keep in mind it's a bit risky. And with these statistics and 200,000 spatial cells, due to the 2E10 velocity space samples in the whole simulation, and this is about 50% of the EGE test case, and about the same as in this ionosphere 3D in the example runs. So again, this is comparable to one of our, let's say, toy models. So that it looks good for in terms of being able to run these with like reasonable costs. And let's look a bit at the time step. And Mercury's magnetic field at the poles is something like 300 plus nanotesla. So the gyro period for the protons would be about 0.2 seconds. And that would give us, considering that we do the 22-degree rotation, the acceleration solver dt would be about 10 milliseconds. And yeah, this just happens to coincide with the solver time step in the Järvinen paper, which is interesting because that is not limited by the gyration of the particles in the same way. Well, in general, there's denser plasma, so we can kind of not look at the wave speeds that much now. So let's look at the 10 milliseconds as the working draft for the time step. And yeah, this is again comparable to our other simulations. like these example runs has 20 milliseconds for the time step. So that's a bit faster cadence, but fine. And then what is the cost per simulated second? And well, twice the time steps needed for one measure of time. So velocity space samples are similar to this case. So we are building on our experience a bit here on the statistics of the old runs. And expecting twice the number of operations per second. And then how long do we want to run? Let's say that we want to run so that the solar wind can flow through the box. Let's say 3 times over, so 300 seconds would be a runner target time, which is also pretty decent for the dynamics in Mercury as well. It operates on a much faster time scale than the Earth. And what we have seen running these toy models, that these are expected to take about 200,000 CPU hours to reach 1,000 seconds, or in that ballpark. And giving some margin and accounting for the twice the cost to simulate the 1 second of this time compared of the Mercury simulation compared to the ionospheric toy model here. 200,000 CPU hours could be actually a decent estimate here to reach this 300 seconds. So that looks suspiciously good. Is there any disclaimers to be made here? Maybe, but let's summarize first. The grid resolutions could be something like this, from 80 kilometers with at the highest resolution, so base grid, some 600 kilometers. Delta T 10 milliseconds inner boundary at Mercury radius, and the inner boundary has been a bit fiddly. If we have the copy condition for the inner boundary, we can have cases where if we drive the magnetosphere strong enough with a dense enough solar wind, it can actually push it to the inner boundary, the magnetopause into the inner boundary. I mean that can kind of happen at Mercury as well, but that's not a very recoverable position for our simulation, so that's not great. So we have to be pretty careful on how we run it, or what is the driving for the magnetosphere. And indeed, the solar wind is a bit heavy and actually a bit cooler than what we usually do. You can see also for the reference the Mercury 5D run with a bit more tenuous solar wind, and this was Markus's solution for now for the disappearing magnetosphere in the 5D run. So yes, this is something that has to be taken into account and perhaps worked around somehow. But in a very fast summary, this 6D run might be very approachable. Care needs to be taken with the inner boundary, but then we do have one elephant in orbit around Mercury, and that is the ion inertial length. So that's pretty small for these plasma densities, and it is going to be quite hard to resolve it for a 6D run. So lowering the solar wind plasma density helps for that as well. So that could be a solution, and try to find some very edge cases for Mercury's solar wind conditions to compare against. So that's a bit hard. Notably, we are not considering now the foreshock here. The baseline cases that we were scaling were all southward IMF simulations. So foreshock will increase the computational demands because then we have complex ion populations in the upstream as well. So that's something to consider. And well, that you can see in the 5D run example already. That is pretty much my slides on this topic. So a very coarse draft on what this could look like. There might be a, not quite sure how well the field solver scales there, but I don't believe that should be the bottleneck anyway there for this run. It has some steep scaling with regards to dx, which Jan can tell us more about at some point if we want to dive into that. But then the floor is open for questions, and after this we can split to different breakout rooms and try and find you some project if you want to run and test those. And for running these projects, we have access for the compute project for some time after this. So we can actually now look at setting you some tests to run, and then you can run it for a few days, and I can also organize some follow-up Zoom early next week and see if you have anything to ask on your tests or any other things that you would like to ask about. So that's my talk this time. This was pretty fast. And yeah, now free error workshopping if you wish. Questions here or online? Yeah, go ahead. So you have the mic. So let's just
the shocks example, where are they anywhere in the example folder?
Those are in the Vlasiator source code. So you can go to Vlasiator GitHub pages and see those.
We have Markus online, so maybe he can provide us a example modern shock config.
What? A more modern Mercury config, do you mean?
No, someone was interested in IP shock earlier when it went past on the slide of Markus.
Yes.
Ah.
And now there is more interest. Continued interest. Do you want to?
Ulf and I said some general things about these IP shocks, but I think you're the best expert on that particular setup. So.
Yes, there are some issues in how it automatically calculates internally the shock gradient. So I think it was that the shock in plane direction needs to be in the XZ plane. That's sadly hard coded, and I haven't had time to fix it. But I mean, it should work. I think the
it compiles.
It compiles. I'm not sure whether I've ran a test now for a while. I think I ran a few tests like a few years back, trying to look at a very large AMR IP shock. Okay, so yeah, it should work.
Do you guys want to workshop it?
Yeah, I can jump into a breakout room.
Yep.
Okay.
So cool. There's one breakout. Yes, throwable mics. They are cool.
I guess this also sort of lead on the interest of the shock simulations, specifically on the events of slams, because I have I recalled you mentioned that the simulations is capable of what, or have you seen any like slant-like structures when running the simulations on the shock?
Yeah, we have seen this. Jonas Suni has done papers on this.
Okay.
So yeah, those are in the 5D simulations where we can resolve the ion kinetics better.
Okay.
For the Earth's bow shock.
For
They
Earth's bow
work
shock,
there. Yeah.
okay. And you guys are focusing on now to develop this on Martian environments?
Not us. That's a collaborator in what was it? Is Hadi in Boulder? I think he's in Boulder. Hadi Madanian is doing this, trying to figure out how to run Mars with Vlasiator.
I guess this the slams that you guys have managed to recreate with the Earth's bow shock sort of tied to the general shock.
Yeah.
Part,
yeah.
Right?
Yeah.
Maybe I just lead on to the interest.
Okay.
With that part of the workshop.
All right. Yeah, then that could be interesting for you to join. So let's have that. Are the guys in some breakout room already? There is Markus Patterby is in room number 3. So yeah, please feel free to join him. And other topics to look at, such as. Okay. All right. Do we have interest on any other topics, or do we just call Markus back to the main hall? All right. All right. Is there online instructors who want to discuss the Harris profile? Being available?
I looked at it, but like 10 years ago, I think Rami Vainio had come to the conclusion that without electrons, it cannot keep in balance, but that's the last I touched it. So, but if there is interest, we can try to get something running.
Yeah. Do you want to discuss this? Do I take it up, or how?
Yeah, was it someone online or is it someone on site? If it's someone on site, you might be
on site. Yeah,
but I can join if you do like yesterday on the sofa or something.
Yeah.
Or
yeah, I guess we'll meet then on the sofas there, and do some breakout room as well. Then do we have other topics of interest? Do we develop more? I think I'll put into Zoom chat that we are dividing up for some. Right. Yeah, I guess that's the largest group so far. So we can actually just call Markus back into the main room and have it here. Hello, Markus. Right, I have the different audio. My audio is going through that computer, not this computer, so I can't help. Yeah. No, I don't actually want to use that. Or this could also work. Moi, Markus. Because now I'm in the different room, so I can actually talk here. Yeah. Yeah. Oh no. All right. So yeah, Markus is going to be a bit delayed actually. Yep. He's working remotely since there's strikes in Finland at this time, so there's things happening around the house. So can someone other pick up the shocks first at the main room?
Well, I guess I can. So is there some specific questions, or shall I dig up some config file?
I guess you can just start with searching, digging up some config, and then.
Okay, because I ran some with
Working out
BC last year. I just have to find them on our cluster. So I'll be back.
All right, and Markus can then join later, and yeah, let's go and look at the Harris sheet. Then I'll be over there, and if there's more questions, you can join. Tag me from my sleeve or ask around in the online thing. There are mics here for discussing with Jan and Markus, so please use those. And I think Jan will be sharing the screen soon here. So if you don't have any projects yet, feel free to follow it here or come join with the Harris thing. So I'll now unblock myself from here. I'll still stay in the meeting and get rid of my mic.
Okay, so I found some files on setting up IP shocks. So you don't really see me, sorry about that. There's lots of snow outside, so it's quite bright behind me. So do you have any specific questions? Because otherwise I might just start rambling randomly, and that's maybe not useful. But so I can. So the idea of the IP shock is that you determine yourself the upstream and downstream conditions you want. So typically we use a Rankine-Hugoniot solver to determine the shock we want in terms of Mach number and upstream and downstream values. And then so this is the one I want to share. Yes, I'll make that bigger. Is that sufficiently big for viewing? Let me know if not. Just don't hesitate to chime in. I don't hear anything, but I suppose it's just no one is saying anything. But shout into the Zoom or into the microphone if you have questions. So we define it with the IP shock project. Typically, we want a dynamic time step. We have some input-output settings here, how often we want to write files. And so in this case, you see that we run a 1D box, which had 1,500 cells in one direction, but only one in the other direction for a certain distance. So you see here we had 200 kilometer resolution. These were like quick tests we run like in an afternoon or so to do some preliminary testing. With pretty decent velocity space resolution here. And so the key point here is to set the transverse directions to be periodic, but not the long direction. And so we have one Maxwellian inflow boundary and one outflow boundary, which will be handled with a copy condition, so Neumann condition. One thing we have not done, and that's a bit because it's a bit tricky to handle in the Vlasov formalism we use, is to have reflective wall conditions. That's a classic thing in PIC simulations of shocks, that you just have an inflow which bounces off the back wall and the shock builds up and travels in the box. And that's a thing which we tried, but it was pretty difficult because we don't have the particles we can just reflect back. We have the distribution function. And so we've much preferred to have the shock stay in the middle of the box, more or less. Of course, as soon as you break the Rankine-Hugoniot conditions, you'll be seeing a slight imbalance. So if you have a very heavy foreshock, that is changing the momentum balance, and then your shock will slowly receding. But in typical cases, the shock isn't moving very much and definitely not out of the box. But that's a thing you'll want to prototype when you do a new setup. So then we continue with the variables we want to write out, how often we want to balance the...
Can you hear us?
Yeah.
Oh, that's cool.
Was there a
This
question
one.
or?
Probably this one is working. Okay. You wanna?
No, is that a question to me or?
I think that is in the meeting. They forgot to turn off the microphone, I suppose. So they are speaking in the room.
Okay, cool. Well, yeah, be loud enough to make sure that to interrupt me. So then we set the standard solution, the standard parameters for the solvers, a sparsity algorithm, and then we say that we want an outflow. So here actually we set a special option here, which says we do nothing to the distribution function at the outflow.
Can you hear us, Jan?
Yes.
Okay, good. I just wanted to ask about the file that you're going through right now. Is it on LUMI anywhere we can find? So we
I could copy it. This was just I found it on the cluster because I remembered I ran some shock tests 2 years ago at some point. But so do you want me to copy it in a?
Yeah, I mean, if we can put it in a certain shape that we can run it together, I think that's what I would like to do. I don't know about the others.
Yeah, can you talk closer to the microphone or louder because I don't hear you that well?
I have the microphone right next to my mouth.
That's cool now. Yeah, I don't know. Maybe it's changing the gain automatically. Now it was good, but before it was a bit weak. I'll just finish going through and then I'll copy it over.
Okay, and also we were having some technical problems with the mic. So can you repeat what you said about the shock itself? How do you initialize it? Does it propagate in the box? What frame is it?
So what we do, sorry, I'll make my phone a bit less loud. Okay, so what I was saying is that we don't have reflective boundary conditions. So one classic way of doing shock simulations with particle and cell codes is to have a reflective boundary condition so that particles bounce and then it starts to build a shock which will then travel into the box. And that's a thing which turned out to be tricky to do cleanly in our Vlasov formalism. So what we prefer to do is the setup like here. So you actually see it on the screen that we have upstream and downstream. So that's U and D here for the conditions for the parameters. And so it's up to the user to determine suitable boundary conditions. So what we do is to have a Rankine-Hugoniot condition solver, like some of us have Python scripts or Scilab scripts or whatever it's called. Not Scilab. I don't know. I used another tool many years ago. But so we leave it to the user. Essentially, what you parameterize is an upstream or downstream condition. If it's in the Hoffman-Teller frame or some other suitable frame, the shock will stay put. But if you're in a moving frame, your shock will move according to more or less the Rankine-Hugoniot conditions. What we've seen, and is probably not a big surprise, is the more kinetic effects you see in your shock or near your shock, the more you're going to break Rankine-Hugoniot. So if you have a good foreshock, that will change the momentum balance, of course. Yes, so that's the parameters. So let's try to just take this one. I'm not sure I can do that from this server, but if not, now, is that LUMI being slow or is it going to... it did work. Okay. So we need this. We need... we need the upstream boundary condition file as well. And so if I go to here, cd example runs. Okay, here IP shock. And so here we have it. Now that config is a bit old, so we're going to check we're going to check if it's still up to date. So for that, we have a tool. I'm not sure if Marco demonstrated it, but we have. I need the binary first, so I'll copy from Apple project 465. And if any of the steps I'm going too fast, just ask me. I'm fine explaining what I'm doing. We had the instructor codes folder, we had Vlasiator, and I guess we have a binary here. Yes, here we have the binary. So when you're preparing to run something like we're doing at the moment, in the source folder, we have a directory called tools. Is it big enough, or should I make it bigger? Tell me if I can make the terminal font larger if you need. We have a script called check Vlasiator cfg.sh. So cfg is short for config. And you pass it a binary, so that's our Vlasiator here. And then we have our IP shock file and the script. We'll check if it ran. Yes. No, it failed to find MPI run. So let's... Because if it doesn't find the binary, we need to run it. What's it doing now? Yes.
This SH file, is it available?
It's in the Vlasiator source in this folder, in tools/check Vlasiator CFG. But apparently there is a fix which we haven't put in the master branch. Apologies about that. Because it tries to. So let me show that that script again. It tries to find AP run, which on some machines is the way to run such codes, such executables. And then otherwise it gives MPI run, but there is no MPI run available either here. So it should. So we can do this. Yeah, no, putting a space should be enough. Why did it not work then? Demonstration effects. This went too fast. Because now it's telling me that all my options are invalid, and that is not correct. Right, we need to have the same modules as we had when building. So let me load the modules we were using to build Vlasiator. So these are listed in the architectural make file as we saw the other day. And if you want me to show that as well, I can. But I'd like to try now. Yes, now our check script is running. Good, and it's telling me that I have these three options which are invalid, and that's correct. We deprecated those a few weeks ago. So I'm going to fix now this example config. Thank you, Lumi. There we go. So the options called samples, we don't have anymore. So we remove that. Yes. And now let me rerun the check script again. So what it does is it parses the config file and it runs the help string, the help option of Vlasiator, and it's a bash script. We just parse it through the options. And so it lists, at the end, the more important bit is telling you that you have no invalid options and no invalid output variables listed. Otherwise, the code would probably crash. And before that, it has a longer section telling you all the possible output variables you could set and you haven't, as well as all the possible options you could set and you haven't. So that's a much longer list. But the more important part is at the end of that telling me that I don't have invalid options anymore. So I believe that now, if I copy a suitable job script from, did we have job scripts in in the example folders? Yes, we have. So let's copy a job script here. Let's see how big we need to make it. I'll check.
Sorry,
Yeah.
this is a bit too fast, at least for me.
Okay.
So now we have the configuration file, the upstream data, and the binary file for Vlasiator to run in this folder.
Yes.
The job, the standard, the sh, or whatever you just did to check what is valid and what is not. Can you say what you did again so we can follow?
So now I opened now the job script itself. So I want to set it such that we can run in a decent time. So what I'm going to actually to make now is make the test a bit smaller, so that we can run it quickly. Oh, sorry, that's my clock here telling me it's noon in Finland. So we'll try to cram it into run it into one node, and we'll try to run it on the debug partition so that we don't queue for too long. And then we need to tell it to use our IPshock config file. So there we go. So now we have a job script which will first run the version string so that we know which version we run after the fact. And then most importantly, it will take our IPshock config file, which I copied in the folder. So now I'll exit this editor and show you again where we are. We are in this IPshock folder, and we have the config file, the job script, the file parameterizing the upstream conditions, and the binary file. And so let's pause now, and I'll take any questions on what I've been doing. There's nothing in the chat at the moment.
Before you edited the sh file,
yeah,
you did a couple of things, and you ended up loading the modules again.
Yes.
What was if we wanted to run the script ourselves, do we have to go through it again, or? Yes.
So what we need to do, so let me go into the source folder. I'll make it clean because there's a zillion files otherwise. So in the source, this is the source folder which you get when you clone the code. We have a folder called tools, and that has a bunch of different tools. And one of, like, some are very old and some are used more often. And one of these is this check Vlasiator config.sh. The one which I run to list valid and invalid options. And that is this script. And at the top, we need to modify that. So I think I'll make an issue, and we'll try to push that in the code version soon, because that's the thing we're always changing. But so you better put a space here instead of trying to run AP run and MPI run, which are not available. It's easier to just put nothing in this line, but that's a thing we should fix. So you can copy this script now from the instructor code folder here if you want. And so if you try to run it without passing the options, it should be telling you the usage. Yes, so you want to run the script and pass it the name of the executable and the name of the config file. And that's what I did in our run folder to check.
Okay, is it possible to put this on HackMD? Because obviously we need time to do these things.
Yeah, sure. But you're seeing the command lines there, right? That's what I was sharing, I think. Or do you see the whole screen?
We see the terminal.
Yeah, okay. So I'll write that up in HackMD. No, let's hope it doesn't get destroyed. So we're on day 3. And I can yes. Wait, I'm on. No, why does it go? It didn't go to the right day, I think. here is the day3 link. Okay. Here we go. So here in the line and give the name of the script. Check. There. And let me paste. Oh. There we go.
I have a quick question.
Yeah.
I'm trying to copy the IP shock file that you made in the Scratch example runs to my folder so I can do the same modifications as you're doing. So I can do them myself. But it's giving me that permission denied. I cannot copy the configuration file and the data file.
And now this is fixed. Sorry, they came as my personal project, as you see maybe on the screen now. So I just changed them. So there should be read permissions on all of that.
Yeah, it works now. Thanks.
And I'd say let's be bold. It seems that it's set up. So let's submit. And then let's check where it is. No, it's not running. Let's check whether there is any free nodes. No, there is no free node on the debug queue at the moment, so we'll have to wait a little bit.
Before submitting the job, do I have to run this file that we edited?
You don't have to. If you're confident your config script is your config file is clean, that's fine. If you've written a new one and you're not sure, it's better to run that to check. Otherwise, I mean, there's different possibilities, but typically, so if you have a typo in the name of the option, so let me open the config file. If you do a typo in any of the things on the left side of the equal signs, it's probably going to tell you unrecognized option, and then you get a nasty error message from the boost library, which we use to parse the options, and then the code just stops. If you have a typo on the right-hand side, and that really depends on the option. We try to be friendly to the user in most cases. There might be cases where the option expects a number, and if you have typed a string, it's going to tell you it can't convert. There's options where it might just do something else. Let's say here, if we take the restart wall time interval, any number will be fine. If you put a negative number, it's not going to write restarts. If you forget that it's in seconds and you think it's hours, you might get into trouble there as well. So it really depends. Like the handling of the options is everything written in the code, and so that's not always completely foolproof, let's say, and sometimes it's very difficult to get it foolproof. But so the left-hand side, whether you have a typo or not, that script will catch for you. And in most cases, if you have a typo, which means the option doesn't exist in the code will crash. So it's just a matter of avoiding. Of course, when we do small tests like here and we're queuing a few minutes, that's fine. When we run production things, we might be queuing for a week before it runs. So you better check your config file before it actually runs at scale, because if it just crashes and you queue another week for just a typo in the config file, it's a bit frustrating. So, but you don't have to run it, of course. So let's see where we are. I'm out of the queue. So something happened and it seems to have crashed. So let's check in the Slurm output file. So this is the version output. I'm skipping through many tens of lines, but here it printed. Oh, that's not too nice. It's missing some input values. So there you see that we had the code printing us upstream and downstream values. That's just we wanted to output those into the output file. But here it's telling us missing input values at line 2 in the file. So, and then it crashed. So then there is an abort call. So apparently we're missing something in that file. So I'll have to troubleshoot that now. If the LUMI file system does not let us down. I'm waiting for the less command to exit. Yes. So let's see. Okay. I think it's trying to do a time dynamic boundary condition, and that's not something I want. So what I will do now, because I don't remember all these options off the top of my head, is run Vlasiator with the help flag. It's a long output, so I'm going to pipe it through less right away. And there you see I'll make it a bit smaller so I can read better, but I'll zoom back once I find what I'm looking for. So I'm looking for so dynamic time step is fine, but I don't want the dynamic boundary condition. So for that, I need to find it's not AMR, it's not. So you see, there's lots of options. So it's best if you start with a config file provided by us or by someone you know, rather than starting from scratch, because there's so many options. We'd spend a week just explaining the options. Here, so now we are at boundaries. It's not an ionosphere boundary. It is not outflow. It's in, yes, Maxwellian. So this has a t interval which defaults to 0, so that should be fine. And this is telling us that by default it should not be dynamic. So apparently there's something with that. So let's explicitly tell it that we don't want the outflow boundary to be dynamic. So that was no, not the outflow, sorry, the Maxwellian. Yes, so this says dynamic is 0, and we want, but that already says it. So then I am really stumped while it wants a second line. So we might have found a slight bug here. So what I will do instead is to just copy that line for a second one. I will put this as the state at 10,000 seconds, so very far in the future. And let's try again then. I remove the Slurm file we had because that was just telling us an error message. And I will submit again the job. And
hello, I am back, and I am mortified by you are doing weird stuff. Are you doing time varying IP shock?
no, it complained about not finding line number 2 in the upstream file. So I believe we have a bug, and I was trying to get it to run for our audience. But then you might be mortified by the fact we have such a bug. No, we still crashed. So now it's telling me missing input values at line 3. And so...
Yeah, well, so the IP shock project has not been run after our time varying merge.
Yes. And so one of us will probably plunge into the source now. But so, yeah, I was thinking maybe putting a second line with a time far in the future will be fine, but that's not the case. Let me run again the help. So it was in Maxwellian. Let's go faster.
We have time varying inflow, then it just reads however many time steps exist in the file. That is not declared externally anywhere.
But so what we have is, so dynamic is set to 0 explicitly in the config file, but the t interval is defaulting to 0. And I wonder if that is not a good thing?
No, that's okay. That's okay.
But so why is it trying to read more than one line? Because that proton Maxwellian.dynamic is 0 even manually in the config file. So I can show you here.
I think the algorithm for reading in those DAT files, I think in the past as well, it just read all the lines that it was able to find, but we just used only the first one.
Yeah.
And that dynamic flag just flips whether we actually try to read any of the other lines, where we try to use them.
We have empty lines at the end of the file. Is that a problem?
It shouldn't be. Do you have enough
so let me resubmit
columns in the file?
Sorry?
Do you have enough columns in the file?
So we have density, temperature, Vx, Vy, Vz, and Bx, By, Bz. Did we add any? This was a working config from 2021 or 22 when we ran these tests with Lucille. So,
well, no, we haven't added anything.
And I just SCP'd it over from the University of Helsinki cluster, so I don't think it broke by SCPing, but let's see if we fare any better. Now we didn't get an error. So yes, and now we have bulk files. So apparently that file parsing algorithm is now sensitive to having empty lines at the end of the file.
Yes, because it sees there's a line here and then it tries to read values for it, but it can't find any. And of course that's a cause for panic. I mean, it's an empty line. The horror.
But so we are now successfully running. So I'm looking at the log file now. We are successfully running that shock simulation. With these settings now we have time steps of 83 milliseconds. The field solver is doing 3 sub cycles. And if I update to the end of the file, we've run 100 steps already since I submitted that.
So this is one of the cases where you probably want to set the diagnostic back to 10 or something. I saw in the config file that was set to 1.
Yes. So diagnostic interval, let's put it at 10, for example. Yeah. Good. So is there any questions, any more questions? So I documented on the HackMD Marcus the usage of the check script, because I run that to check that we had the velocity samples and spatial samples invalid options. However, we still have a non-working version of the script in the source repo. We should fix that line about MPI run and AP run. I thought we had fixed it, but apparently it hasn't made it yet. Yeah.
Yeah, just want to clarify things. So these on the HackMD, you mentioned this check file. So before this, am I supposed to copy this IP shock folder from the example runs into my own directory and then copy this check file into that?
Yes, that's better. You can also just run the script from there with instead of putting the // before check Vlasiator config, you can run the full path. That's fine as well. But yeah, please, if you're trying now to run yourself a shock test, then do copy it into your own folder so that we don't run simultaneously in the same folder.
Okay. Yes.
I'll add a link on HackMD to Analysator script, which is used to calculate the Rankine-Hugoniot conditions for these IP shocks. It doesn't, of course, give the exact. It gives the MHD-based Rankine-Hugoniot conditions for the shock, and that is what we usually use for the initialization of these IP shock runs. But what it results in is a simulation where the shock does not necessarily stay stable in the middle of the box, because Rankine-Hugoniot is calculated for MHD and not for a kinetic situation. And yeah, you don't want to look at that. That is an IDL script.
Yes, but by yourself as well. But that's the old one, so I guess.
Yeah, I mean, what was it, 2017 or something? I think that one actually it should be deleted, because I think it might have some errors. I've rewritten the script a couple of times over, and I'll place it here in HackMD, the one that has last been used successfully.
Now, so what we can do, are people interested in actually seeing what comes out of that simulation? I could fire up my visit and show you how to do that in visit. Or you can also use your own visit if you have a working one, or you can use your own Analysator if you'd like.
If I may ask, can you show your upstream file? So upstream.bat.
Yep, sure.
Just to see what kind of modifications you did.
Yep. I actually didn't modify the upstream from what. Well, I mean, it's the one which is there. So you see the command line?
Yes.
So that's it just contains these. Was it 8, 9 values?
Okay, but did you say that there was a new line that we had to remove in order for the code to run?
Yeah, so let me actually check from where I copied it. So that's now on the yeah. So you see here that there is an empty line, at least one empty line after that that line, and so that seems to be now. So this file, if you go to setting up a time dynamic upstream boundary, that's a bit advanced and it's a very recent thing. We only included that now in the course of the last year. It will read these lines consecutively, and the first value is the time. So if you put 0 and 10, it will linearly interpolate the state of your boundary condition between the times of 0 and 10. And so now the algorithm is a bit dumb in the sense that it just looks at the file, it looks how many lines the file has, and it reads them in sequence. And so that's why it was complaining to us, because it read the second line, but it was empty.
Okay. And just
so if you compare now to this, it has no further line. It just says here there's one line.
Okay. And for each values, I understand that from the right to the left, we have 3 magnetic field components, 3 velocity components, and then
yeah, and then it's the
500,000
temperature in Kelvin, and the density in inverse cubic meters.
Okay, and this is all ion quantities, so ion temperature and ion density.
Yes. So so if we go back to the config, so here we define that we want it to be protons, and they have a mass of 1 in units of proton mass and a charge of 1. So you could, if you wanted to, you could define, say, alpha particles and tell them a mass of 4 and so on. But remember, it's all hybrid, so
yeah.
Yeah, so you can set the electron temperature to be used by the electron pressure gradient term. That's in the field solver settings. Probably not in this file.
Yeah, we didn't have it set here, but Marco had a slide on that a bit earlier. If you want to explain more, there were some questions too on that. So. But indeed, so you can set, yes, so Marcus, actually a question we got earlier was about, so we knew the answer in the sense, the question was whether the polytropic index is the same in the whole box. And it is at the moment, at least.
Yes.
But there was, I didn't hear that well, it was in the room there, but there was comments on the fact that in some settings, it's known to be different in different places of the simulation.
Yes. Not in different places of the simulation. The polytropic index, if you evaluate it from spacecraft measurements, then yes, it will be different in the solar wind, at the bow shock, in the magneto tail. Tough.
Yeah, that was the suggestion, actually, to use values from empirically determined from spacecraft measurement. Let's say in the solar wind and magneto sheath, use the adiabatic value 1.6, and then at the shock use an empirically motivated value like 1.4.
Yeah, that's a nice idea on surface value, but then there's the question of, well, how do you build an algorithm which knows which value to use where, and how do you scale it from region to another, or a dynamic simulation that builds up from a uniform box? So
if we're simulating a shock, one can use the algorithm for the active mesh refinement to determine the highest gradient at the shock, and then use...
but that's not only at the shock. It will refine the mesh wherever there is something interesting going on. So, I mean, yeah, this is open source software. Feel free to start toying around with ideas like this, and we are, of course, happy to, if you get something working, then to take it into the code base. But one of my jobs is to say to ideas why they might not work. And here, exactly the question of defining regions. It's not straightforward for something that's going to be dynamic. Like, what if we have a tilted dipole suddenly, and how do you treat the bow shock versus the flanks, and all sorts of questions. So for our purposes, to be honest, the electron pressure gradient term is minuscule, it has negligible effect on mesoscale or global dynamics. I mean, I've run two simulations where one of them had the shock gradient, the electron pressure gradient term off, and the other one had it on, and you plot them side by side, you can't tell the difference. So small details to the adiabatic term. On a global level, I would not be concerned about it, and just saying 5/3 is a good approximation. But yeah, I mean, feel free to try and build something better.
So I suggest to make this now, to modify this test, because we see that it's fairly slow. I forgot to scale it down to run faster. So let me show how we could go on about that. And we could also set the gradient of electron pressure term into the next iteration so that we see in the output files whether it is how big it is.
Yeah.
So what I'll do first.
It's true, it might be different for IP shock.
Yeah, well, the resolution, let's not make the resolution too coarse, but I'll change some parameters. So first, I don't want to continue this test, so I will use the kill command we have built in the code. So I say touch kill. This creates a file on the disk. And we see now that this file was renamed with the date when it was taken up by the code. And if we check at the bottom, at the end of the log file, we see that it exited. If we issue a kill command, it doesn't write a restart file, it just exits gracefully. And it's a bit nicer than going to cancel the system's job. If I run the SQ again, we see that the job by Kempf, so my job is gone at the moment, or right now. So let's go back to modifying the config file. So it was a bit slow. I'd like to make it a bit lighter weight since I'm running on one node. So what I'm going to do is let's keep the number of cells. Maybe let's stay at 200 kilometer resolution. But since I'm prototyping, I'm not too worried by having a very, very good velocity space. So what I'm going to do is cut down on the resolution. I have now 134 blocks per dimension, and I'll have that to 67. And that should roughly make us a few times faster, like not quite 8 times, but it will be significantly faster here. And then let's go to the...
Can I clarify one thing about the box size? So are you running here a 1D simulation?
Yes. So this at the moment is 1D because I said that there is one cell in Y and Z. But we can change that. So
if I want to make it 2D, I simply increase the length in whatever direction I want. Right?
So for example, let's say we want to... this is not going to fit on one node anymore, probably, unless we tweak some other parameters. But I could say that in Y, I want 100 cells, and then I make it that size.
No, you don't do that, Jan.
No?
Not in Y, in Z.
Sorry.
Yes. No, my apologies for the project being limited in that fashion, but it doesn't work properly if you try to extend it only in Y and not in Z.
But then I'd suggest that we make the resolution twice coarser, just so that we can still run it at a decent speed. So let's say we have 750 cells in that direction and 50 in that. And so I need to make my extents like this for the Y dimension. And in Z, we go to 5v6. If I wasn't... that should make the cells cubic still. Let's not write a file every half second. And let's say we write a file every 5 seconds. That will be enough for our tests. Let's save some disk space and not save velocity distribution.
That's not going to be cubic.
Sorry? Is it not cubic?
I don't think that's cubic now.
So what did I do? No, you're right. Should it be 1E7 here?
define the cell size and the cell counts, and then calculate the sizes. I think none of the three coordinates matched just now.
So I kept the box size and I have the cell count. Well,
where do you see the cell count?
So the problem on that is I think that 750 cells, but 300 million meters. How does that really?
300 million
Okay,
meters
that's
divided by 750 cells. That's 400 kilometers. Yeah. So we have 400 kilometers extend in the y direction.
That's good.
And so 50 times, well, let's just do it. That would be 220 million. And we divide by 2.
Okay.
So that's,
okay. Now it is good.
Now we're
yeah.
good.
Okay.
Okay. And so let's save this. I will check in another file. Did we have? Yes. For the grad PE term, if we have it set in that file. Field solver, yes. So let's just copy these values from this file and paste them. So we go to the field solver section of this config file and let's paste the values here. Now the electron temperature should be matching the proton temperature, shouldn't it, Markus?
Not necessarily.
So I keep this.
You might. I mean,
those are the upstream proton values as well. You see, we're not
for magnetospheric conditions, I think the electron temperature is usually approximated to be 1/4 of the proton temperature. But for solar wind values, actually, I don't know.
Okay, but we should also then write out the variable. So do you remember off the top of your head how it's called?
VGE grad PE. I think so.
There we go. So we have that. Let's check if there is 3 nodes on the small queue. There is 1 node.
Run the check config script.
Let's run the check config script. That is a very good suggestion. And we have no invalid options there.
Aha!
What?
No,
we're expecting
no invalid options. That's great.
Yes.
We are not hopeless.
So let's remove the old vlsv files we have here so that we see what we're doing. Let's remove that kill file and the old slurm file. And but yeah, so we made it quite a bit bigger, so I'm not sure it's going to fit. What does the debug queue say? That's the kind, there's 8 nodes free. So let's modify the job script and say can we run 4 nodes on debug? I think we can. Let's try to see if we can fit it in 4 nodes. And so we can check here, and indeed we are running. And so let's see. Yes, the log file got going. No, that's the log file from before. We are still setting up. We have the version output. So I'm looking now at the slurm output file from the system. Yes, so it's printing now the shock conditions we have put in. So I believe now in the log file, yeah, we see the current time, 12:42. And we started running. We're doing about 1 second per step, so it's pretty fast. You see now that the time step is longer. It's 159 milliseconds now because we have a coarser box. Like the grids are a bit bigger, so we can run for longer steps without crashing.
This is a major difference between magnetospheric simulations and IP shock simulations, because our global time step in magnetospheric simulations is very strongly limited by the gyration of particles from the strong magnetic field of the Earth's dipole, and that strong magnetic field also affects the fields over time steps. But for IP shock simulation, then translation has a significant role in determining the time step because gyration is usually quite slow.
So is there any questions on the last steps we did?
I have a question.
So now we see, for example,
on the last
sorry, yeah. Say
I
again?
have a question, but not on the last step.
Yep, go ahead.
Regarding the input.
Yep.
So you said that we need to initialize the simulation. We need to set the upstream and downstream conditions according to Rankine-Hugoniot. But in the DAT file, you only put the upstream conditions. Doesn't the code itself use those conditions to calculate the downstream values according to Rankine-Hugoniot? So
no.
From us as users, do we have to put upstream and downstream?
So I'll show you so I went a bit fast. It's in the config file. I think it's near the bottom. So here we have
a point of clarification. In the config file, we set the generic simulation conditions, and that includes here now we've got the IP shock project, and the IP shock project can set the conditions throughout the simulation box according to certain calculations. In the SW DAT file, or the upstream DAT file, we are setting the conditions for one of the system boundaries, the upstream inflow boundary. We don't set a downstream outflow boundary value because those are the copy condition to ensure sufficient outflow from the box, and they get actually assigned according to what is here in the IP shock and proton IP shock values to start with, and then they evolve from that.
It's actually not a copy condition in this config, but it's a different boundary condition nevertheless. So the reason we do this is that we didn't want necessarily, it's probably that we didn't want to code Rankine-Hugoniot solver in the Vlasiator code, and we can put it in a more customer or user-friendly way and say, you're free to set the conditions you want. So we don't force you to be in the Rankine-Hugoniot approximation, nor do we force you to be in the de Hoffmann-Teller frame. If you want to do a traveling shock simulation, that's perfectly possible. We actually did such kind of simulations recently to check that our adaptive mesh refinement was following the shock going into the box. But so from the code point of view, we don't force anything. There is only that the in-plane components have to be in the X and Z components. So that's a limitation of the code that we don't that the Y component isn't taken into account here. But that's about the only thing. What we do, and Marcus, correct me if that's wrong, but the width is given here, and that's, I think, a tan-H step. I'm not sure we can change
It's not a tan-H step. It is a smoother step function. Okay. Because a tan-H step does not, it asymptotically approaches the values towards the upstream and the downstream, whereas a smoother step function has a limited width after which it is a constant value. It's close to a tan-H, yes.
Yeah, so that's what we have in the code, and I think that's not available to change as a config option. But once you have your own copy of the code and you build it yourself, you're free to change that if you want to change it as well. So
yeah,
but so
one of the reasons we don't want to have a Rankine-Hugoniot solver in the code itself is that, as I alluded to previously, Rankine-Hugoniot conditions are evaluated using MHD, and we are simulating kinetic physics. So the energy balance at the shock in a kinetic shock simulation is not the same as the MHD approximation. So quite often what you get is that if you put in the Rankine-Hugoniot conditions, you get something that's close to having a balanced upstream and downstream, but not quite. So if you need to adjust your shock conditions so that you actually get the shock to remain in the center of the box due to all the extra kinetic physics, then it would be a real shame if the project wouldn't support that.
And so I decided now to start my visit. As you see, it's not any faster for me than it is for you guys, even though I installed it. But so we should be able to look at some output files. Yes?
In the meantime, if I may ask another question.
Sure.
So now the input is set in the configuration file.
Yep.
And if I understood properly, the upstream.dat file just sets the condition at the upper boundary. Why the redundancy? Why the code doesn't take the input from the config file and use that as?
That's partly historic. So the code we took inspiration from an MHD code at the Finnish Meteorological Institute was also using this config file for the boundary condition. One reason is that it's a bit more flexible because we can have these line by line, and especially thinking of time varying, if we'd have to put so the boost library we use for passing the config file reads a pair of option n value. And so we'd need to have one line for each of the parameters, so density, velocity x, velocity y, velocity z, and so on. And then we'd need to multiply that by the number of timelines we want. So it's a bit more convenient to have a separate file for these boundary conditions. And if you think of cases where you have not one, but maybe 2 or 4 of your walls where you want to have a set of parameters, it becomes, I mean, not that our config files are very easy to read now because they are very long, but it would be even worse if we had to have that in the config file as well. But so it is a bit redundant, but on the other hand, what you could also do, and that we do in some tests, is that you have a certain set of conditions in the box as defined in the config file, but then you have a different set of input conditions from the wall. Say you want to push a pulse into your simulation, and you could set that in the upstream file and have that then propagate into the box. Some of these tests are admittedly more of technical nature, but I mean, there is also, say, if you want to have a traveling shock or traveling perturbation moving into your box, you could parameterize it in that upstream file as well.
We've actually used it in the past before we had fully time varying inflow conditions that could interpolate between these different lines. What we could do was we simply swapped out the SW.dat file for a different one to trigger instantaneous pressure pulse going into the simulation domain. But yeah, so there is indeed an extra level of, if you're changing the parameters, you need to change 2 files instead of 1. Historic momentum or conservation of historic momentum here.
Hello, may I ask one quick question?
Sure.
Yeah, I also do some philosophy simulation. I'm wondering, how do you determine the domain in the velocity space, and how do you determine the resolution in the velocity space? Yeah.
So this is, it depends on the type of distribution you want to model. But the usual guideline I gave is that assuming you take a Maxwellian, and that's typically what we have in the code as well, look at your thermal velocity and make sure that you have a sufficient number of cells, so of sample points of your thermal velocity, so the width of your distribution in velocity space. Now, what is sufficient is dependent on a number of things. For like quick testing like we do today, I'm not too worried. So if we only have a handful of points to like sort of have a Maxwellian, that will be fine for the demonstration purposes. Once you're running simulations, you'll want to assess whether you have a lot of numerical diffusion. So if you go too coarse in number of points you have in velocity space, by numerical approximations and the mapping algorithm we use, it will tend to heat up pretty dramatically if you're too coarse. And that you'll see in your simulation. It's well possible we'll see that in this shock simulation as well. I can demonstrate what I mean by that in a few seconds. So let's plot the density of our simulation. Let's just do the full plot like this and see how it looks. So as we parameterized, we have a rather long box with a bit of cells in the transverse direction. So now this is a full 3D object, so it's a bit clumsy to plot. But you see right away that we have a high density region, a low density region. I'll zoom to show you that there is a smooth transition there, but then we don't have a lot of cells across that transition. So it's only apparently like 4 cells from one side to the other of the shock. Now for slightly more convenient plotting, I will add a slice operator and draw that. And then it resizes the aspect ratio of our plot to the screen size to make it slightly more friendly to us. So this is the T0 setup. And so we see that at the upstream and at the downstream boundary, we have also the same values as in the box, because that's how we have parameterized our upstream file. And so how do I move away that zoom thing? Can I move it? Is it? Yes, here. So if I click on this arrow, we'll go forward in time. Now we moved by 1 step. But let's do the reverse and go to the last time step right away. So at the moment, we've simulated 65 seconds. We seem to have some structure forming here. We see that the shock step isn't exactly at 0 anymore, but like for these 65 seconds at the moment, we're still staying in the box and not breaking dramatically. I'm not sure you see it over Zoom, but there is some small changes in this side. So there might be some foreshock forming. We'll see how it evolves.
That's a quasi-parallel shock, right?
I must say I don't remember, but I believe we had been looking at wave transmission near a shock, so that must, I guess there's going to be a foreshock forming. We can look at the config, of course, and put on the physicist's hat and not the supercomputer hat. So yes, there is an oblique component, so we will definitely start seeing things happening. So let's see in the let's go back to visit. If I hit reopen, it updates the state of the database, and then we can move forward. And now we're at 95 seconds, and this is how it looks now in density. And then, of course, we can look at any other, whoops.
I think you had the non-thermal density also available. How about that? That would show you any backspring particles.
So let's see. We have the reducers for the non-thermal part. So let's look at non-thermal density. So how this works.
Jan, just for information, when you're doing this visit plotting, then at least on my Zoom, the context menus that open up sometimes don't show. That we could see is like going to proton, but then any of the variables under the proton so-called were not visible.
Okay, let me know about these things. I'm not sure how visit behaves on Zoom too well. I will make the annotations bigger, and then you see the variable names on the plot a bit better. So
I think the color bar annotation is decent. We can read it there. It's just the pop-up menus which can be.
Okay, well, now this is a bit too big maybe. But so Marco went pretty fast over this non-thermal, so let me explain it again, especially in times of, in these kind of foreshock simulations. What we do, or I can actually also pull up the config file for that. I believe it's set at the end here. This proton thermal section is what we're interested in at the moment. What we do in the code to determine what we call thermal and non-thermal part of the particle moments is we take a center. So here is the drift velocity as we decide to parameterize it. And these are exactly the same values as the upstream values, as you see here. And we give a radius in meters per second. So this is a radius in velocity space. And so at the moment, at the stage where we compute the moments for writing out into the file, we do the calculation for everything that's inside that radius, and we call that thermal. So you have to make sure that this is around your solar wind population, and that this radius isn't too big, so that it's not going to catch too much of the backstreaming foreshock population. and everything outside is we call non-thermal. And so that works if you have set these parameters to match properly your foreshock. Of course, if you go into the downstream region, and that's what you see here, a big chunk of your distribution function will be in the non-thermal part. So this data reducer, this variable makes no sense in the downstream region. We want to look at what happens in the upstream. And so I'm going to do this now to change the limits of our colored of our plot to see what's happening in the upstream. So it's all in that blue, and I assume that there is not much more than maybe caps lock, 1E5 per cubic meter, so 0.1 particle of backstreaming per cubic centimeter. And indeed, it looks like we have a foreshock slowly forming and streaming up here. While we talked, I assume the simulation runs further, so let's update this, move forward, and now we're at 115 seconds, and indeed we start to see foreshock waves forming also in this variable. At the moment, clearly it's pretty smooth in the vertical direction, so it doesn't seem like we're getting 2D effects yet. I'm not sure we'll get any at this resolution, but possibly if we wait some more. Any questions on this plot and this variable? Otherwise, we could try to inspect what the gradient of electron pressure term is telling us.
By the way, for this simulation, do you utilize some flux limiter?
Yeah, the field solver is using limiters when calculating derivatives. Otherwise, it wouldn't be that stable to simulate shocks.
Yeah, indeed. Okay, so.
Yeah. So, further questions? Otherwise, I'll just modify that plot a bit. I'll actually hide this one. Maybe we'll reuse it later, and I'll add a new one. And we want now to go into here it is, the electric field grad PE magnitude. The slice operator is valid on this plot as well. And so now I'm not sure, well, let's zoom because you might not be seeing much in the over zoom. So let's increase resolution. And so here we see that there is one slab of cells, which is red. That's the peak value of 0.1 millivolts per meter. And that's at the shock, and everything else is a lot weaker here. But still we have the value. Now we can compare with the electric field magnitude, and this peaks at 2 millivolts per meter. So we have something like 5%. So actually at this resolution, it already starts to have maybe some significance. When we look at the global magnetosphere runs, we have the resolution at 1,000 kilometers. And there, the gradient of electron pressure term is somewhere in the microvolt per meter. So there it's like 3-4 orders of magnitude weaker than the rest of the electric field components. So there we run with it, but then we can tell referees that at this resolution, it doesn't play a role. Now in this IP shock setup, as we see, we have finer resolution, and it may be not too far from being actually doing something more useful to the physics, the grad PE term. And the finer we go, the better we can. So at the moment, we run 200 kilometers. We're running on, 4 nodes on LUMI. So if you run something bigger, you can accordingly also increase your resolution and try to see what effects are coming into play, which wave modes start to be more important, and so on. Any more questions? What was the timetable? Yeah.
So I'm running on my folder the 1D simulation just to see how things would look like.
Yeah.
Visualizing in Visit such 1D simulations, can someone extend the other dimension? Because I made this pseudo color and it only gave me a single axis without any color scale. I plotted, for example, the magnetic field magnitude.
Okay. I don't hear you too well, so stay close to the microphone. One option, so do you want to share on Zoom or are you on site without Zoom?
I am on site, but I can log in on Zoom.
Okay, so if you want, you can share. One thing you can try is hitting this button with the green cross. That's resetting the view. So if I do it now, we're going to have the full box again, because sometimes Visit is a bit confused and plots things too far out. And the next question is, do you have a slice operator? Because when you have a very stretched box, it plots you the thing in 3D because we have a logically 3D grid, even though it's a 1D physical setup. And that might be that you see only the axis because the box is so thin and long that at the zoom level you're at, you don't see the actual thing. So that's what I did also in this case here for our viewing comfort. So I added the slice operator. So that's in the operator menu and the slicing and then just the normal slice operator. And that stretches the aspect ratio to fit your screen. And then you might be able to see your 1D better. But so yeah, if you want to join us on Zoom and share, we can do that. Otherwise, I can try to find your files and plot those as well, as you prefer.
Yeah, the slice operator works now. It was
All right.
zoomed out. Thanks.
Okay. So what does it say here? So we have, no. There is no lunch break. We just keep talking until conclusions. Okay, right. So we can keep talking some more. Any other questions? Would you like Marcus to show us how to plot this in Analysator? If he's still around and not.
Yeah,
Running away.
that would be nice.
Sorry, Marcus, are you fine with me throwing the ball to you?
Yeah, sure, we can give it a go. Let's see. Just starting the job.
In particular, yeah, see, yes, my microphone is still in. In particular, we might try to fish some distribution functions. Since we have a foreshock forming, we might be getting some nice surprises there.
Yep, we can look at those. Sure.
And actually, if we have time and if people are interested, I can show the procedure with vlsv extract as well. So the command line tool and then plotting in Visit. But let's first have the Analysator demonstration now.
So just waiting for it to start.
I believe I was pinned earlier. I'm not sure if Marcus is now pinned in the room, or do you see him big as well in the room? Like his screen view. I guess you see his screen then.
Who knows? Let's see. You are still pinned, but I think a screen share takes precedence. So connect to Jupyter. Dumpty dumpty dump. Okay. So let's see. Set the directory. So it was it example runs and IP shock. Is this the one, Jan, where you were running? Seems like it. We've got.
Sorry, I lost my Zoom window. Yes, it's there.
Okay. So I'll just. What? Ah. There we go. Delete that. Might as well start from this. Row non-thermal is actually good. Let's go with that, and I'll delete the F saved. And I forgot a comma, and I forgot something else. Okay, so it wasn't vlsv deal. Let's see. It was file deal, which needs to be. I'm clearly in Friday mood. Okay, there we go. Let's see, we've got the Warhol color scale. Let's change it to Viridis. Let's lose the watermark because it's taking up quite a bit of space here. And let's scale things down a bit. Get you as well. No, I don't. There we go. So with the scale keyword, I can scale down the text a bit, which is nice in that it can actually then give more emphasis to the plot itself. Let's see. Okay, but do we have an aspect keyword? Maybe not. Let's go to a linear scale. And automatic scaling. And scientific notation off. So we've got we've got this situation where indeed it is saturating here in the downstream. So Cmax, let's put it at 0.1. Is that giving us anything more interesting? Not yet. Of course, we're at step 1. That's why we went
5.1 seconds. Yeah.
Yes. So let's go to step 20. There we go. That's looking a bit better, but let's zoom it up still. Okay, now we're already saturating all of that region, so we're overstepped. This looks more like it. And now we will not be able to plot any PDFs because I have F saved 1 and I'm not seeing any PDF contours there. So can I actually launch a terminal here?
We have an X stride and Z stride of 10, but a Y stride of 0. Should that have been 1 then? The out of plane stride? I'm not sure, but the config has some stride, so I'm a bit surprised. I probably just forgot to save the variable. Yes, VGF. No, VGF saved is saved. What does it look like then?
Yeah, because I think F saved is always on, but you don't turn that variable.
Yeah, you do. But it's 0 everywhere, so for some reason we managed not to save distribution functions.
Oh dear. Well, it's a fast simulation. Let's see. New launcher, terminal. Oh, what's this? Athena? Do I have a better launcher? No.
I'll do a touch stop so we can restart because it's actually hit the 30-minute mark now. Let's see. Too late. Damn it. The run just ended.
There we go. No, I don't have Emacs. I'm unable to operate.
Module load nano. Do you want me to do it?
Okay. I can look at it here.
Yeah.
Maybe if we find out what the issue is, then you can edit the file. So,
well, I believe the y-line stride might have to be 1 instead of 0.
maybe. So the right t interval is 5. But yeah. Yeah, okay. I thought it was okay to leave it at 0 for a singular dimension, but maybe not. So you can edit it and give it a go. Let's see if I can come up with something interesting otherwise.
Do we want to change any parameters for demonstration purposes, or is there anything in the room or in
let's see. We can add outputs. So you've got F, G, E, and B. You've got populations, densities, tensors, velocities. You've got E by PE, boundary type, rank, blocks. Yeah, I guess that's good. Solar wind energy density. Nah, maybe that's too much. Let's see. Good. So let's make the vectors a bit smaller.
In the meantime, can I ask a question about the simulation I'm running?
Sure.
And visualization and visit.
I don't know about that visit stuff. I'm a Python man, but maybe Jan can answer that then. But yeah, no, I can also try to help with that. Go ahead. Do you want to share your screen?
Yeah, if possible.
Sure.
Okay, this is the initial 1D simulation that the code was configured for before changing to 2D. And it's the same upstream and downstream conditions. So this is a quasi-parallel shock. But when this is the color scale is density, I think. And then the vectors here, I don't think you can see them clearly. They are magnetic field vectors, but they look quasi-perpendicular. So am I doing anything wrong visualizing the shock here?
Well, one thing is that since you are doing a 1D simulation and you are using Jan's trick of setting it to slice, which changes the aspect ratio. And if you look at the x-axis, you have an extent of, 300,000 kilometers. And on the y-axis, you have 200 kilometers. So I would say that the vectors probably are in the correct direction, but they just get squished by the aspect ratio. So if you give the screen back to me, I can show you.
Yeah.
Because that is what I just now happened to do, is I plotted the magnetic field vectors here. And this is now the 2D simulation, but as I said, it should be the same parameters. And what I did was I turned on the vectors, made them a bit smaller so that they are easier to see and they don't cover up the actual background data. And then I zoomed in. So the box size is now from -5 to 10 Earth radii in the x-axis direction, and the full extent in the y-axis direction. So what the Python plotting scripts is that they retain the aspect ratio unless I think there might be some way to break it by force, but that's usually not a good idea, because then you get these questions of, well, what does this vector look like? It looks like it's completely incorrect. But So this is now the whole simulation 2D domain that Jan was running. And then indeed, when we zoom into a situation closer to the bound shock, or to the shock, then we see that, okay, we've got, it's not a quasi-parallel quite, well, maybe, heading towards oblique, and then you can see that in the downstream, the vectors they get squished together like that, so then they point even more to the side. And sadly, we do not see a lot of wave structure there yet. We can try to vector density. I think the default was 100, so let's go to 500. Yep, we get a lot more of them. And if I look here, how many bulk files do we have? We have bulk files up to 34. So what I was doing here is I set the file directory, and then I just give the step. And I hate this scrolling bar that we get in Jupyter. But so here now, actually, we do get something a bit more interesting. Let's zoom in even more. Let's go from -3 to 3 in the X direction like that. So now you can see that we are starting to get upstream wave oscillations. The magnetic field vectors vary in the upstream. We're not seeing structure in the Z direction yet. That will come with time, probably, depending on the ion gyro radius in the upstream versus the box extent. But you can see that you are starting to build up actual plasma waves. So I hope that answers your question.
Yeah,
if you
thanks.
if you turn the slides off and actually just manually zoom in, then you should be able to see the vectors in the correct direction there.
Great, thanks.
And I'll add that
I could also say thank
visit-
you for the questions. It's so nice to actually have people asking questions instead of just the Finnish standard silence of a training event.
I believe visit is automatically plotting only the in-plane components, of course, when there's a slice. So if your slice was in the XY instead of XD, that might be also why you only saw then the... But yeah, so the slice operator...
that's not it. That's not it, because it was the X component that was getting squished away.
Yeah. Okay, so it was an aspect ratio issue. So yeah, now we're rerunning, and we should have the first distribution functions coming in, if I didn't do mistakes.
Yeah. Okay, there we go. So we've got file number 2 is a new one. Okay. I'll just copy that and copy cell, paste cell below, and let's get rid of the vectors like that. And let's get rid of our zoom in. We still don't have any PDFs.
Visit now is giving me an error. So everything was running fine, but after a certain time step, it started giving me an error that the engine has exited abnormally. Compute engine running on LUMI has exited abnormally.
So, wait, is my microphone on? Yes. I tried as well. My engine also crashed. I think it's because the files have changed. So if you hit reopen and start a new engine, it should work. I see, Marcus, that the first 5 files are like 130 megabytes instead of 14 megabytes. So I believe we have something stored.
Okay.
But why...
I had my I didn't change the step, of course. Thank you. Ta-da! We have given our simulation measles. So we have the plot PDF command here right below. Let's start using that.
So you can use file index 5 if you want. That's on disk.
Okay. So let's see, what coordinate position do we want? Actually, let's zoom in a bit more there. Let's go to -5, 5, -5, 5. And let's see, so Earth radii 1 would be here. So if we take half, then we're getting right nicely. Well, let's take 1 for the coordinates. Then it'll be in the upstream, and we will get a smidgen of reflected particles there, I believe. And then we can just set those to 0 and it'll find the closest. And let's see what this looks like. So we are that, and oh boy, there we go. 25 seconds. Solar wind core backstream particles. Okay, I'm going to get rid of the watercolor map. Let's do plasma.
Hello,
That should be a bit easier on the eyes. So this is what we have here. We have the solar wind core, and we have backstream particles that are gyrating. And if I can duplicate the command and do the perp as well. And yeah, this is now integration. And while in the other direction, it of course looks just like a blob. We don't have any partial crescent shape structures here, it seems. But what if we do that as well as para, but then do a slice instead of the integration? Okay, there seems to be plenty of stuff there as well. Yeah.
So sorry to interrupt. We have some people who are running off to the next meeting pretty soon, and I mean we have still only basically half an hour left of the nominal workshop time anyway. So just to take a moment to formally conclude this, and then maybe if there's still more questions, then the rest of us can hang out for a bit, I guess. But as it is, let me get rid of leave the breakout room where I was hanging out.
Another thing, in case you haven't been informed, you will have access to LUMI for a week from now to continue your projects.
Yes, that's. I was going to mention that. So I was thinking to we have still a bit of time to run on LUMI or these training exercises or whatever test cases you might want to do. We could have a follow-up Zoom next week. I'm suggesting on Tuesday. Is that fine for people? Is anyone interested in such a thing? Afternoon, I guess. I can send a doodle or something through to put that up on the study materials front page, for example. So we can have a chat next week on your discoveries. My email is markku.alho@helsinki.fi, and we are, all of our emails are like first name and last name at helsinki.fi, so feel free to pose questions to us afterwards. I can be kind of the main contact and then deal out further if you wish to ask general questions. And then I did a quick feedback form for us, and I put the link up as well somewhere. So yeah, feedback is will be appreciated. And if you want, you can also note there if you want to have more details on some different topics, so we can think about having more themed workshops maybe later. But that's left for the future anyway.
Yeah, this was, I think, our first workshop for external collaborators like this, or possible future external collaborators. We've done training events for our own summer interns and, of course, onboarding new team members, but this is the first one of this kind of format, so we are very happy to hear any feedback that you might have.
Yes. Do we have any other comments from online instructors or participants? Something in the chat, I guess. Sounds good. Yes, it does. I concur. All right. I guess then we can conclude with the official business and let the ones who are running off to the next meeting get going. And I'll stop my share here and start putting these links up somewhere. So thank you for attending and thank you for your interest.